Hi guys, my name is Joseph Ejike Oji. I'm here with you again. I hope you are enjoying my lectures. Tonight, we'll be discussing dependent events, independent events, and the multiplication rules. I hope you are ready for me. Let's start with dependent events. Two events are said to be dependent. Let's say that we have two events A and B. They are said to be dependent if the occurrence of event A affects the occurrence of event B in such a way that their probabilities changes. Look at the good examples here. Let's say having good grades and getting a scholarship. So if event A is having good grades and event B is getting a scholarship, when you have good grades, you get a scholarship. They are dependent. One affects the other. How about this? Parking in a no parking zone and getting a parking ticket. See? So when you park your car in a no parking zone, you get a parking ticket. These two events affect the other, and so they are dependent. Okay? Now, for independent events, two events A and B are said to be independent if the occurrence of event A does not affect the occurrence of event B. See? Example, if you win a Maryland lottery, that does not mean that you win New York lottery. See? Why? Because they are totally independent. How about this? The fact that Mr. James got a job in a Bank of America does not in any way affect Mr. White getting a job in Bank of America. They are totally independent events. See? Because none of them affects the other. There's one thing when we discuss independent events, which is sampling with replacement. When you select from a group and put back the number that you selected, or the card that you selected, or whatever that you selected, you still have the same total. The total did not change. So we say that sampling with replacement are independent events. I'll give you an example. A playing card, we have 52 in a deck. If you remove one card and put it back, you still have the same 52 cards, so that nothing changed. And if you calculate the probability of any of the card, it will still be the same. So we say that sampling with replacement are also a good example of independent events. Okay? Now, having given you this background, we are going to calculate the probabilities for independent events and for dependent events. But for this lecture, we will focus only on the independent events. Okay? Now, before that, let's see this is what we use to calculate the probabilities of dependent and independent events. We call it the multiplication rule. According to this rule, when two events A and B are independent, the probability of both of them occurring is given by this formula. Probability of A and B equals the probability of A times the probability of B. Now, some books will use the sign that we call intersection sign for here instead of an and. They all mean the same. Okay? Now, if there are more than two events, you can even extend the formula. For example, if there are three of them, you can say the probability of A and B and C occurring becomes the probability of A times the probability of B times the probability of C, and so on and so forth. Now, this is the formula for independent events, the multiplication rule for independent events. Let's try some examples here. Look at this example. It said a coin is tossed and a die is rolled. Find the probability of getting a head and then rolling a 6. This is a coin. A coin has 2 sides. Dice has 6 sides. Okay? So the outcomes that we have here will be 2. The sample space for a coin is 2, and for the dice is 6. So the formula now will apply the multiplication rule here. Probability of head and 6 becomes probability of head times probability of 6. For a coin, the head has 1 out of 2 chances, which is right here, 1 over 2 times. For the dice, only 1 6 is there, only 1 6. So you're going to be 1 out of 6 chances. When you multiply them, you get the answer you have there. I can show you on the calculator. You can see 1 over 12 will be, let me open it, clear it. 1 divided by 12. Okay, 12. And that will give us, I press the equal sign. See, give me this number here, which is what we have here. Okay? So this is one example of how to use the multiplication rule of probability for independent events. Let's try another example. It says, the probability that a particular knee surgery is successful is 0.85. Now, you know that 0.85 means 85%, okay? Said, find the probability that 3 knee surgeries are successful. So there are 3 of them. So let us say that S represents successful. So in this case, they give us the probability of successful already. So all we have to do is to apply it here. The probability that the first knee is successful, that's S1, and the second knee surgery is successful, means S2, and the third knee surgery is successful, S3, is P of S1 times PS2 times PS3. That means 0.85 times 0.85 times 0.85, giving us 0.614. Okay? Yeah. So you can see, like I was telling you in my previous lecture, the formula we use in statistics sometimes they can look like a monster, but when you use them, you see that they're actually simple. Okay? Okay, look at this example. It says, approximately 9% of men have a type of color blindness that prevents them from distinguishing between red and green. If 5 men are selected at random, find the probability that all of them will have this type of red-green color blindness. Okay? Now, we hope you are ready. Now it says they give us the probability as 9%. They give us that 5 men are selected, which means we are going to extend the multiplication rule into 5 points. That means let us use C to represent red color blindness. Now, the probability that the first man selected, I mean C1, has red color blindness, and the probability that the second man, that is C2, has red color blindness, and the probability that the third man, C3, has red color blindness all the way to C5 becomes PC1 times PC2 times PC3 times PC4 times PC5. That means you're going to multiply all the 9%. But before you do the multiplication, you have to change the 9% to decimal. That means 0.09. So that you have 0.09 times 0.09 times 0.09 times 0.09 times 0.09. That will give you this answer right here. See? Very easy, right? I told you it's simple. Now, I've been giving you examples that are more direct. Let us try one example that is a little bit challenging, and I'm sure that you're going to enjoy it because I'm going to make it as simple as possible for you. Okay? All right, let's look at this. It says, the result of 985 pedestrian deaths that were caused by accidents are presented below. See the deaths, the information here, the statistics here. Pedestrian intoxicated, yes, no. Driver intoxicated, yes, no. So it says, choose 2 pedestrian deaths at random with replacement. Now, he said with replacement, which means that this is independent, because if they select and replace, we still have the same total of 985. So they are independent. He said, find these probabilities that they both involve intoxicated drivers. B, that both the driver and the pedestrian was not intoxicated. So before solving this kind of problem, what the first thing you do is to find the totals. So that means 59 plus 79 gives you 138. 266 plus 581 gives you 847. 59 plus 266 gives you 325. 79 plus 581 gives you 660. So we add 325 plus 660 gives you 985. And as a check, you can add 138 plus 847 will also give you 985. With this, you are ready to do your calculations. The first one says they both involve intoxicated drivers. That means if you select 2 pedestrian deaths, that they both involve intoxicated drivers. Let's calculate it here, over here. So he said let P be pedestrian is intoxicated, and P complement means pedestrian is not intoxicated. Let D be driver is intoxicated, and D complement means driver is not intoxicated. So the probability that both the driver, that the accident, look at what it says here, they both involve intoxicated drivers. So the probability that the first driver is intoxicated and the second driver is intoxicated, or the first death involve an intoxicated driver and the second death involve an intoxicated driver, becomes PD1 times PD2. Now, for intoxicated driver, we go to the table. How many of the drivers are intoxicated? See, look at here. Yes, we have total for. See, this section is for intoxicated and non-intoxicated driver. See, so you see driver intoxicated. Yes, we have 59 and 78, which is 138 total, out of a total of how many deaths? 987. So total for all the intoxicated drivers are 138 out of a total of 985 deaths. That's how we got it right here, 138 over 985. Now, because times D2, so it was saying that both of them are intoxicated, which means that you repeat the same thing, 138 over 985. So 138 over 985 times 138 over 985 give us 0.0196 or 1.96%. So we have 1.96% chance that the accident involve, that pedestrian death involved 2 intoxicated drivers. Okay? Hope I made myself clear. Now, second question says that find the probability that the driver and the pedestrian was not intoxicated. Okay. Now, it means that both the driver and the pedestrian were not intoxicated. The quickest way to solve this is I tell my students to draw a line, and I will show you that in a minute. First of all, let us write the formula. Formula is right here. The P, that the driver is not intoxicated, that's D complement, and the pedestrian is not intoxicated, P's complement, is the probability of that DC at D complement times the probability of P complement. Now, how do we get the complement? Remember, in my other lecture, I told you that I explained that the complement means the opposite. So being intoxicated, the complement is not intoxicated. So that's why we are using DC and PC, where DC is for the driver, not intoxicated, and PC for pedestrian, not intoxicated. Okay, I have it here. Driver intoxicated is no, all this way. So I normally tell my student to draw a line here. Then pedestrian intoxicated is right here at from top, but not intoxicated is right here. So driver not intoxicated, draw a line. Pedestrian not intoxicated, draw a line. You can see that they intersect at this point, which is 581. See? So that gives us 581 out of 985 pedestrian death times, because it said both the driver and the pedestrian are not. So you use the same intersection. If you go to the table, you see right here, no and no. And this is the point right there. That this is the point that represents both the pedestrian and the driver are not intoxicated. Put it right here, then multiply it. Some students ask me, how do I multiply this kind of thing? I told them it is actually simple. If you have a calculator, I can show you right away. So first of all, I turn it on, and then clear it, then put parentheses first of all. Okay. The first one is 581 over 985. I have 581, okay, divided by 985. Then I close the parentheses, times. Then I put another parenthesis so I can put this one here, the second one, 581, which is 581 divided by 985. I close the parenthesis. See? So that when I press the enter key, it gives me the answer point. You can see right here, 0.3479, which round up to 0.348. 0.348. So that we have what we call 34.8% chance that it involves both the pedestrian and the driver are not intoxicated. I hope you enjoy my lectures, friends. In my next lecture, we'll be talking about multiplication rule applied to dependent event. The one we just concluded is multiplication rule applied to independent event. But in my next lecture, it will be multiplication rule applied to dependent events. All right. I will see you in my next lecture, and once again, thank you for listening. Remember to subscribe to my channel so that you get notifications when new lectures are available. Thank you. Bye-bye.